Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Marcelo Miller Bertolami with us today. Hey, Marcelo.
Hi, thank you for having me here, and hi to everybody out there.
Well, thank you so much for talking about your very lovely article. And Marcelo, where are you located at? And what's your geolocation?
So I'm in La Plata in Argentina right now, so in the southern hemisphere, and it's pretty warm and humid right now. So that's why you might be. It's not. I'm a bit nervous, but it's not the only reason why I'm sweating right now.
Yeah.
So
Well, because you have your summer shirt on, that's why. So it must be quite warm there. So um yeah, it is February 16th of 2023 as we record this. And while it's summer in the southern hemisphere, it is definitely a little bit wintry here in Phoenix where I'm at. So we were definitely a little cool this morning. So all good. Marcelo, do you play guitar?
no, I don't. I would like to play, but I don't. I really don't. Unfortunately. Yeah.
Very cool. Well, it's a nice guitar. It's a nice little painting over there right there. Did you do that painting on the right?
No, that's from a friend of my girlfriend. So that, yeah, and
Cool. Very cool. Very nice. Awesome. And Marcelo, what do you like to do for research?
so let's say I started and I was forming in stellar evolution. So I usually do stellar simulations, numerical simulations of stellar evolution of low mass stars, usually like late stages of low mass stars. That would be. I started at the very end because I started with central stars of planetary nebulae, and as I grew up, went backwards. And since let's say in the last 7-8 years, I also started to collaborate with some friends on planetary formation. So
Cool.
mostly evolution of protoplanetary disks and the formation of planets around that. So
Very cool.
astroseismology is the other thing. I mean, as part of the stellar evolution thing, astroseismology was one of the big things. I collaborated with some of my supervisor at that time and now friends.
Cool. Very cool. And that is going to bring us to this very lovely.
Which in a way it's a bit different from what I usually do, because what I usually do is very detailed numerical simulations on a computer, and this is more of a toy model. So
Yeah.
this is a
Well, it's breadth. It's got some, different angles to it. So very cool. So this is an APJ article. It's open access, people. You can go get a copy for free. Go get it. A Red Giant's Toy Story 2. Understanding the Red Giant branch bump. And Marcelo, take us away.
yeah. So why is it, as I said before, this is a toy model, and in a way it starts with the previous paper. I will just make a comment of why I did that paper and how that took me to this one in particular. Is
Okay.
that so the previous paper was really trying to understand why stars become red giant. That was what it in principle, it sounds like a trivial thing to do, that something that we already know every star does. But when you look at it in detail, it's not so clear that we really understand it. I mean, this is very common in stellar evolution. It's very easy to come to something that looks like an explanation, but it's really not an explanation when you look at it in detail. So, for example, it's very common regarding this red giant thing. So it's very common to hear, let's say, stars becomes red giant because as the core contracts, it releases energy. This we want to say something. Yeah. No. Oh, no. I was saying that it's very common to hear this kind of explanations, like, for example, as the core contracts, it releases energy, the energy is absorbed by the envelope, and then the envelope expands. But it looks like a reasonable explanation, but when you look at it in detail, it's really not that of an explanation, because
Okay.
first of all, the energy released by the core is really meaningless in comparison with the burning that released by the burning shell, and the envelope has no way of telling one from the other, for example. It also, yeah. So this is one of the things. The other thing is very common to hear, for example, things like as the stellar radius becomes large because the burning shell increases in luminosity. But
Okay.
it looks also reasonable, but when you look at it in detail, it's not much of an explanation, because why would the burning shell increase its luminosity out, the energy output? In principle, the temperature of the burning shell could settle slightly bit outwards, and then nothing will happen because luminosity will be much lower, nothing will happen. So it's very common in stereo evolution to come to these kind of things that look like a reasonable explanation, but when you try to really pinpoint what is the cause and what is the effect, it does not. So that brought me to try to, me and many others. So, I mean, to try to figure out a simple toy model in which you can see the things at work. So where you could see how the mechanism operate.
Okay.
So in the previous paper, what I did was try to do this kind of analytical toy model of how this happens. You can go to figure 2 if you want, but in principle I can. So from that paper, let's say the takeaway thing is that what I found is that in principle the conditions set by the envelope in principle in a way constrain the temperature of the burning shell. And they create a relationship between the temperature of the burning shell and the mass and the radius of the core.
Okay.
Okay. If you take into then if you add the thing, if you want to say something, just please interrupt me.
Oh, I'm good. I'm just interacting as you go.
And if for example, when you add the thing that the burning shell has to also at the same time is the main contributor to the luminosity of the envelope, and the fact that it also has to transport the material there has to transport that luminosity. Then you also add that then this adds a pressure dependence on the mass and luminosity, in the mass and radius of the core. And together with the previous one, this means that in a way the density of the burning shell itself has a dependence of the mass and radius of the core. Okay. So this in principle looks like nothing so important, but then when you think about it, this means in the global thing that as the burning shell starts to be a burning shell, so once the burning shell is ignited, this means that the density at the burning shell has to follow a particular dependence on the mass and radius. Okay. And this means that, of course, this means that, for example, the mean density in the central parts in the core, it evolves with the mass so mass and inverse to the cube of the radius. Okay. But this means that then the dependence of those two densities on mass and radius follows different powers, and then homology contraction is not possible anymore. Okay. And this is very important because this is what will create, in particular, will set the fact that you don't have only one scale, one length scale. We have everything cannot contract on one length scale because things cannot contract homology. So this creates constraints that break homology. This is the main takeaway, if you want, of the paper. Okay. Then if you add the fact that for low mass stars, you also have a mass radius relationship. You know that low mass stars evolve as the degenerate core increases its mass, and the radius stays more or less constant. And in high mass stars, this is also the fact you have that the mass is more or less constant and the radius decreases, contract because the core is contracting. So in these two different stars, but the mechanism is the same. Density, the ratio between the density at the shell and the density at the core is evolves in different way. It diverges in a way, and this creates the conditions to put to create the red giant. So I came up with these equations, and then I wanted to test it. And this is how I made a more detailed model of a low mass stars, in particular because that was the easiest thing that I could, which is in a way depicted in figure 2. Figure 2 in this paper in a way shows this kind of simple model of a low mass red giant, in which you have a degenerate core. Yes. On top of this degenerate core, you have a region that behaves more or less like ideal gas, so isothermal mantle, yes, which is composed of an ideal gas at the temperature of the burning shell. And on top of that, you have the envelope. Yeah. So, and this thing that is marked as outer mantle there, which is immediately above the burning shell, in a way is the one that is relevant for our paper, because it's really not, the burning shell itself does not feel much what happens far away, but it really feels what is happening immediately above. And this you could see in the equations if you want. So this was the simple picture that then I computed. Let's say I tried to compare this with the detailed stereo evolution models, because this is an easy one, and then I got a good agreement. So once I got a good agreement for the low mass, then I said, what can I apply it for? Maybe we can use it to understand other things, and this brought me to the red giant branch bump. And let's talk about what the red giant branch bump is. So if we can go to the figure 1, that's perfect.
Figure 1.
Yes. So So this red giant branch bump is this zigzag that is, there's this, you see the diagram there, and then you have this zoom in region. So as stars evolve away from the main sequence and into the red giant branch, so the thing on the right of the diagram, you have this tiny, you don't see it in the but if you zoom there where you have the cursor, then you see that there is this particular region where the star stops evolving upwards, and suddenly it starts to decrease its luminosity and then again increases. So in a way, the star on the red giant evolves upwards, downwards, and again outwards again. And this is a very peculiar thing that was discovered already in numerical simulation from the 1960s. So in 1967, Thomas was the first to publish at least it, and then Eco even in 1968. Also found it. And so the reason why that happens, although it was clear in the simulation that it was happening, the reason why it happens is, as I mentioned before, finding causes and effects in stellar evolution can be tricky. So then some discussion starting on why this is happening. So I think that Eco, even in his 1968 paper, he mentioned that this is this decrease in luminosity is a consequence of the fact that, and so what? Let me go a bit backwards. Why this happens, or at least what is specific about this region, and why you find this thing at that particular luminosity? So we know that this is related with the fact that when as you see, the structure of a red giant is very simple. At least low mass red giants are very simple. You have the generated current below, a burning shell, and the envelope. That's it. So the reason why, in principle, as the burning shell increases its luminosity, the star increases its luminosity, because everything is in a steady state. Nothing is very rare, or nothing is evolving faster. Everything evolves in a very long time scale, a nuclear time scale. So in particular, the thing is, as the star evolves away from the main sequence into the red giant, then the convection develops in the envelope. So you have a convective envelope, and this convective envelope becomes deeper and deeper. At least at the beginning, it becomes deeper and deeper, and this creates at some point it becomes so deep that it goes into the region where nuclear material was already processed by nuclear reactions on the main sequence, at least partially. Convection steers everything and mixes everything very, very quickly. So this gives you a homogeneous profile. But whatever is left below the maximum penetration of the convective envelope is not mixed. So you have a jump in the chemical profile of the star. What you see is, and you can see that in figure 4 in this paper, because I think that might be useful to give an idea of what is happening inside the star at this particular phase.
Okay, here we go.
There. So these are, one is, you have these two diagrams. One is in the mass coordinate, and the other one is in radius. I'm used to look at them in the mass coordinate because that's what we usually do. And so what you can see there is that what you see there is the hydrogen content of each layer of the star as a function of the deepness or the mass coordinate of the radius, depending on which one you're looking at. And as you can see, there is this whatever is below the burning shell is the final drop in the hydrogen profile. That's where the burning shell. These three colors are showing three different snapshots of the evolution. So what is left when the star the convection goes very deep, you have this kind of like it's a purple. If you can zoom in the lower figure, that's I think it will be easier.
I will do that.
If you look at the purple profile, then you see that it has like two steps. The lower steps is the hydrogen burning shell that is really depleting the hydrogen, and then farther away, closer to the surface at about 0.24 in this particular star, then you have another step, and this step is what was left by convection. So convection mixed everything that was to the right of this was mixed by convection, and everything to the left was not mixed by convection. And then the thing is, the burning shell goes as it burns the material, it proceeds to burn farther and farther away, and at some point it reaches this discontinuity, and it's at that point this when it reaches the discontinuity, and we will see the details later, that the luminosity drops. And this is, and once it goes through the discontinuity, it starts to increase again. So then you have this evolution that we saw, that the star increases its luminosity, it drops, and increases luminosity again.
Yes.
So this is what is causing it. So we have a good idea since the 60s that this happens at this particular time for this reason, but how it happens is not that clear. So as I mentioned, even in his 1968 paper, he mentioned that this is due to the fact that there is more hydrogen fuel, and this lowers the luminosity. It's not easy to understand how this is the mechanism would work in such a condition, but yeah. So then later you had the Schweigart in, I think it was in 1990, a paper. They look at it in more detail, and they realize that the drop in luminosity does not happen when the burning shell reaches the discontinuity, but earlier. So when the luminosity starts to drop, the burning shell is not really at the discontinuity, but slightly below the discontinuity. So it could not be the fact that whatever the mechanism is, it could not be that the fuel of the burning shell is changing. I mean, the hydrogen content at the burning shell is very similar. So they concluded, or they guessed, that it might be the opacities above the burning shell that are doing the thing.
Yes, yes.
Okay.
I'm with you.
But you also have another explanation that is very, in a way, compelling to a certain extent. That is one put forward by Rethal and Weigand in the 70s. That is an homology analysis of the thing, in which, in a way, if you make this kind of shell homology relationship, and you can see them in equation so that you give an idea, is what equations 1 to 4 are, this kind of relationship. Yes. When you, under certain relatively simple hypothesis, you can say that the density at the burning shell, the temperature at the burning shell, the pressure at the burning shell, and the luminosity above the burning shell. This is a bit tricky to what exactly they mean, but they depend on the mass of the core, the radius of the shell, and the mean molecular weight at the burning shell, which is not very well defined in that. So that's a bit, but let's say the mean molecular weight. We can go into the details later. So the interesting thing is the mean molecular weight is the mu there in the equations. So the explanation by Rethal and Weigand was that, as the burning shell reaches the discontinuity, it reaches a region with a lower, a lower mean molecular weight, because it reaches a region where there is more hydrogen. The mean molecular weight drops, and as there is a very high power dependence of the luminosity on the mean molecular weight, which is, at least in a very simple computation, it like the luminosity goes with the 7th power of the mean molecular weight, so which is a lot.
Pretty good. Okay.
So they say, okay, it reaches a region with lower mean molecular weight, luminosity drops. And it looks like a very good answer to me, at least. But there is one caveat, which is not minor, that if you do the numbers with this kind of number, if you just look how the luminosity drops with the mean molecular weight, you put the mean molecular weight, and the percentage that the luminosity should drop is much higher than what it drops actually.
Okay. Okay.
So it looks reasonable, but the numbers do not really work out very well. So as I said, the explanation for this thing, even there was a paper even recently in 2020, I think, by Saskia Hecker, when they tried to look at how the entropy changes in time as the shell reaches the discontinuity.
Yes.
But the conclusion is not easy. Also, I think there are reasons why it's not easy to do that, because the fact is these models are almost in what we call thermal equilibrium. I mean, it's not really an equilibrium; they are in steady state. So really, changes in time occurring in such a long time scale that looking at the entropy changes probably is not going to be the most insightful. But interestingly, as I said, the Rethal and Weigand explanation, this shell homology relation explanation, is interesting and it looks reasonable. And there was a paper in 2015 by Jürgen Christiansen where he showed that in fact what this mu should be is some kind of effective mu, and so the fact that in a way this simple putting the mean molecular weight at the burning shell or immediately above the burning shell is not the right thing to do. You should do something like integrate outwards and get some kind of mean value of the mean molecular weight.
Okay.
And put that thing there. And that's interesting because, of course, when you integrate outwards, then you could see what this mean molecular, this effective mean molecular weight is equation 12, I think. And
we'll get to 12. Just looking at that. There we go. There we go.
Yeah. So there. Well, you see that in a way the mean molecular weight transitions smoothly between the value below the discontinuity and above the discontinuity as the burning shell approaches the discontinuity itself, which are these radius S and radius this. They are in the equation. Okay. And this mu up and mu down are the mean value above and below the discontinuity.
Yes.
So interestingly, then if you put this into the Shell model simulation, they improve, but they do not improve as much as you'd like them to improve. So it's still, I mean, a factor of, I think it's a factor of 3. I mean, it's written in the paper, I don't remember. So it's off by maybe too much, but it improves the situation.
Okay. Yeah? Good, but not good enough. Okay.
I think that the explanation, this is the explanation that you find for the red giant branch bump in for example, if you look at the Kippenhahn, Weigert, and Weiss book, the classic book by Kippenhahn, this is the kind of explanation that you find for the why why do you have this drop. And so what I said, okay, I have this model of this simple toy model of low mass stars that I did to check my explanation of red giants. And I said, okay, I can try to use that to get some more insight into this problem. And this is the main thing of the paper, to try to use a simplified red giant, low mass red giant model to understand whether this is the right explanation or not, if you want. Okay. So if we go, and I can give you why the idea happened. We can go to figure 2. That I can in a way give you an idea of what are the missing ingredients in this explanation.
So where do you want me to go? I'm sorry.
Yeah, figure 2.
Figure 2. I'm sorry.
Yeah.
There we go. Figure 2. Back to our favorite. Okay.
Which is colorful, so it's also nice.
It's very cool.
So, as I mentioned before, one of the interesting things, the properties of the core, usually sometimes one forget that the red giants have this particular, the core of a red giant is, there is this degenerate core, which is in particular in the lower part of the red giant branch, the evolution is so slow that the core really is almost at the temperature of the burning shell. So because there is no extra energy released by gravitational contraction, because everything is going too slow. So but you have the degenerate part of the core, which takes almost all the mass of the core. But when you look at the radius of the burning shell, the radius of the core is not really given only by this degenerate part, but the mantle, this isothermal mantle on top, plays an important role because it has almost no mass, but it's really at very low densities. So in comparison to the core, so it really occupies a rather large volume, if you will.
Okay.
So, and the interesting thing is that this mantle is at the temperature of the burning shell. I mean, it has to have the temperature of the burning shell because it's almost so. It's in contact with the burning shell, so it's really at that temperature. So the interesting thing is that if whatever you do to the burning, if for some reason the burning shell increases its temperature, yes,
okay,
this will at the same time hit this isothermal mantle.
Yes.
Yes, and this means as this is an ideal gas, this will expand.
Sure. Yes.
Yes, and this will mean that the radius of if you try to hit the burning shell, the mantle below will expand, and this will push the radius of the burning shell outwards.
Okay. Okay.
And this is interesting because from the toy model and also from the explanation of the red giants, one of the important things is that the temperature of the burning shell depends on the mass of the core and on the radius of the burning shell. So if you push and in particular it goes to the inverse of the radius. So if you push the burning shell outwards, it decreases its temperature.
Yes.
So if you increase the molecular weight and this increases the temperature of the burning shell because of the Joule-molecular relationship. You cannot neglect the fact that this hits the isothermal mantle and pushes the burning shell outwards, and this will have an additional impact and decreasing the luminosity because it will decrease the temperature, in fact.
Okay, I'm with you.
I mean, it doesn't mean that the net result will be that the temperature will decrease. I'm not claiming that. You have to do the numbers for that. What I'm meaning is that if you look at the mean molecular weight, and the mean molecular weight goes down, then this will, on the other hand, decrease the temperature. This will make the isothermal mantle more compact, and this will have an additional effect on trying to increase the temperature of the burning shell.
Sure.
Yes.
Yes.
So there is a competition between these two things. So the idea was, let's do the numbers and then add this additional thing. Let's add the feedback from this isothermal mantle.
Okay, cool.
And this is what is done in section 3.2. So if you want to look at the first equation is equation 13, which is just laying out the shell-homology relationship result.
Yes, that looks like homology. Mm-hmm.
Yes.
Correct.
So as you see in equation 13 and 14, you have this thing that the changes in the luminosity are proportional to the changes in the mass of the core. Yes, which is increasing because it's burning something. So, but you cannot neglect. And then you have an effect on with the opposite sign, which is the radius. So if the radius increases, the luminosity drops. And then you have the mean molecular weight. So the usual thing with the explanation of shell-homology relationship only involves the last term, which is the one with the power 7, because the core does not increase that much. So,
right.
But now what we are doing is, okay, but now we have this simple model where we can compute how the changes in radius depend on the other things. And this is what is done if you want, it's done with equation, let's say equation 15 is what comes from the toy model I developed to explain the red giants. So and you can see that you can see that there is a constant, and you have powers of the mean molecular weight of the envelope, powers of the radius of the shell, powers of the mass of the core, and then there is this exponential with more dependencies of the mu, so the mean molecular weight of the envelope and the radius. So if you just do some math, so you make some perturbation, so you try to see how things change at the given position when you change the mean molecular weight. Okay. Then you are left with equation 17. So if you put the numbers of what is happening at the red giant branch pump, you end up with equation 17, where you see that changes in radius of the burning shell, when you take into account the typical mass radius relationship, what is below, and the radius will change more or less as a percent, let's say 60%, 66% of the changes in the fractional, the relative changes in the mean molecular weight. Of course, the number there, it depends on which kind of opacities you assume, exactly what is the mass of the core, exactly what is what is the mean molecular weight, the point at which you are, but it does not change that much. You put some other numbers and you end up with 0.64, 0.66. So it's really not
around there, right?
Which is, for me, that's great because I don't like details. So.
All right.
So the interesting thing is now, if you go back to the previous equation and you just plug that into the what we were looking before, so we end up with equation 18, equation 18. Which in a way summarizes the main result of the paper, which is because if you compare equation 14 with equation 18, you see the difference is that the power, or here is not power because these are relative changes.
Yeah, relative changes. I'm with you.
Relative changes.
You still got the 7, yeah.
But the 7 that was in front of the mean molecular weight now is half of it.
Yeah.
So now. If you add this thing, then how much the luminosity will change when the mean molecular change drops as a consequence of approaching the discontinuity is much lower because it's really a factor of 2 there.
Okay, I'm with
and
you.
If you add whatever Jürgen did before that, he really realized that this was an effective mean molecular weight. Yes, and now you compare these changes of this simple model with with the detailed evolution code, you find out that the agreement is very good. Now is really good because now it's down to a percentage. I mean, I think it was. Let me check here, but I think it was the. What was the
32%, 30%?
Yeah, I think it was around 30%. I'm not finding. Yeah, so it's here it's 32% less than the actual. Of course, if you put different opacities, but the opacities are here are almost Thomson scattering, the electron scattering opacity. So it's really they are not huge changes that you can expect there. So. And this is, I mean, this 30% discrepancy between a very simple model and the detailed numerical evolution, that's something I can go with. I mean, for me, this is almost a perfect agreement, to be honest. Because this is really a toy model with almost very few physics. And to me, this really confirms, first, that the explanation comes from the fact that the mean molecular weight changes, but you have to add these other nuances, yeah, the mean molecular weight is not really the mean molecular weight immediately above the burning shell. It's really a kind of mean value that comes from looking at this outer mantle region, which is not the whole envelope. It's only this region next to the mantle that you have to integrate, and then in a way the mean molecular weight changes less because it's a mean and it changes more in a progressive way. It's not a sudden thing. It's really a progressive thing, then you have to add the fact that the core in a way reacts a bit. At least the outer part of the core reacts to the heating or cooling of the burning shell, and this changes the radius, and this adds this additional layer. So this, in a way, this is the main part of the article. I think the fact that if you add the feedback from the inner isothermal mantle into the shell homology relationships, and you take into account that the mean molecular weight of this shell homology relationship is a mean value, that this was already done by Jürgen in 2015, then the agreement is
very nice,
very good in my opinion, at least. So once I did this, the next thing was I thought it was interesting, at least from a pedagogical point of view, if you want, to do a very simple description of how this happens. So the next section is really a simple description of the branch, of the bump itself. Now, one thing I didn't mention at any point is why is it called the red giant branch bump? Because it is. We can leave them for later if you. But this is so because the observational counterpart I never mentioned. I forgot to mention it. So
yes, exactly.
So, so I will do it now, and then I can make it. So the thing is, this is called the red giant branch bump because when you look at a globular cluster, for example, when your population, let's say, is something that is close to a single stellar population, something that was born at the same time and with the same metallicity, and you look at the globular cluster and you look at the red giant branch, and you start to count stars by you beam the stars by luminosity on the red giant branch, and you count how many stars you have there. One of the first thing that you see is that, of course, as you go to higher luminosities, there are less stars because higher luminosity red giants they evolve faster because they have luminosity which are maybe 2 orders of magnitude larger. This means that they are consuming the hydrogen at 2 orders of magnitude higher, and of course this means that the star is evolving 2 orders of magnitude faster. But this is the first thing. You look at stars, and then in the lower red giant you see a lot of stars. In the higher part of the red giant you see very few. But there is a bump. There is a bump there. There is the thing is almost monotonous, but there is one bump, and this bump it looks curious, but it's the reflection of the thing, because what you see here is that the star goes up, down, and up, and so in a way it crosses the same luminosity 3 times.
Right.
And of course, this means that if you are binning things by luminosity, then you will have 3 times, or more, close to 3 times. It's not really, but more or less 3 times the number that you have in the neighboring values. So when you count, you see this monotonous decrease with luminosity, and on top of that, this 3 times the number of stars, which is the reflection of the fact that the stars are going through that luminosity 3 times.
Yes, right here, cut across.
No, that I forgot to mention. Sorry,
It's all good.
So So the simple explanation, so which was just to close the paper, was let's do something that, in a way, we can show that this shape, this is usually this is how the luminosity of the star changes with the mass of the core.
Okay.
This is figure 5? Yes.
Figure 5.
Yes, this is just the same behavior that we saw before, but just plotted as a function of the mass of the core. So, and as star evolves, the mass of the core increases because the burning shell is adding more and more mass to the core.
Yes.
And what you see here is and if you put those, sorry, what I did was a simple equations if you want to show them, but these are equations 20, equation 20, where you see that you adopt a very simple model of how the position of the discontinuity, I mean, let's say the position of the burning shell and the position of the discontinuity, they are related with the mass of the core in a very simple way by this kind of linear relationship. It's not really a linear relationship because and so you adopt this, which is just the consequence of the fact that as the star evolves, it burns, so the shell gets closer to this continuity. And if you put that into the previous equation, then you find that this mean molecular weight that the shell sees is a function of the mass of the core, so which is equation 21.
Yes.
And if you put that on the shell homology relationship, now going to the shell homology relationships, you have that the luminosity of the burning shell changes with the 7th power of the mass of the core, that we knew, this is the standard thing, and on the mean molecular weight now is represented by something that is also a function of the mass of the core.
Okay, good.
Yeah,
I'm with you.
Yes. So, and this is what is plotted in figure 5, in fact.
Okay.
There you see how the luminosity of the burning shell, the luminosity of the burning shell and of the star, because the envelope has a constant luminosity. So whatever is generated by the burning shell goes out at the photosphere. So this is the same thing. Is the luminosity of the burning shell and the luminosity of the star are the same thing. So the two purple things are, I think, for two different assumptions of the opacity, I think.
Yeah.
And you see that the behavior is more or less the same. And so the upper part is the change in the luminosity as a function of the change in the mass of the core, and the lower part of this plot is just the change in the mean molecular weight.
Cool, very cool.
So what you see there is exactly that this, first of all, that is the drop in the luminosity, in a way the departure it starts before it starts to really go downwards. It starts to slow down and then it goes down. Right. And this is really a consequence, and this happens always at the nuclear timescale. There is nothing that is contracting at the fast pace. Everything happens at the nuclear timescale. It happens at the core growth. So I think in a way it clarifies a lot how this zigzag happens. It happens on nuclear timescale as the core growth, and in a way the luminosity of the burning shell reacts to these constraints from the shell homology relationship. The fact that you approach a region where the effective mean molecular weight is lower. This increases the temperature of the shell, but also not as much because the inner part is expanding. And then this gives, and the green thing there is not the simple model. The green thing there is the detailed stellar evolution model.
Sure.
So there are differences, of course. There are quantitative differences between, but the agreement is quite good. So you see that the shape, and at the time at which the shape departs from from a straight line, that is what you expect if there is no mean molecular weight change, is the right time. So
cool.
And so this is the simple thing, which I think is very nice, because at least something that always frustrated me when I was studying stellar evolution is not having toy models, not having things that I can teach someone. No, honestly, I
get it.
And in particular, not with the red giant branch thing, but with the red giant branch question, if you want. I was very frustrated for many years because at first I thought it was me that I was not understanding the things. So, you are taught this happens, and then you see, but I'm not really getting the thing. Why is really, and everybody has an explanation, and when, as I mentioned at the very beginning, they look reasonable at first glance, But when you try to really pinpoint the causes and effects, you realize that they do not work, or they are asking for the answer in a way. The explanation itself it implies that you assume that the answer is right. So
sounds circular.
Yes, this is one of the main. In fact, in one of these, I mean, in one of his papers about this red giant, why stars become red giant by Eco Even in 1993, he mentioned that all these arguments are circular, so that you have to be very, very aware that many of these supposed explanations of the red giant thing, they bite their own tail, you know.
So to say, that's a nice way to say it. Very cool. Very cool. Very cool.
So, and I think that on one hand, I'm happy because this, in a way, I think it inspires me some confidence in the kinds of model that I created to try to understand the red giant thing, which is the big question that I really like to understand. Nice. I already saw when I was doing the first paper that this toy model of a low mass stars gives a couple of things that are very interesting. First of all, it explains why the radius of the burning shell stays almost at the constant value, because there is no reason why it should be like that. I mean, in fact, in massive stars, it's not like that.
Yes.
And if whatever is below is a white dwarf, it won't be like that anyway. Also, because the white dwarfs contract as they increase their mass. So,
very cool. Very cool.
So, and this is, and also, yeah, I think it, to me, this kind of toy models, they really clarify, for example, this thing. In a red giant branch star, the main thing, why does the core increase its temperature? It increases its temperature mostly because, I mean, at the end, it's also contracting and releasing energy, but at the beginning, it's really heating up, mostly because the burning shell is heating up.
Yeah.
Yes, it's really the burning shell, because it's really the burning shell that is driving the temperature changes in the core, not the other way around. So this is
absolutely.
And I think that with these kind of toy models, you can see them in a simple way, and more importantly, I think that you can explain them in a better way. For example, now I feel much more confident, I think, to a certain extent, to the extent that I can be confident about what I found. That in the sense that I can explain with simpler words what the stars are doing. Cool. Because the problem with numerical simulations, in particular detailed numerical simulations, that the ones we do in stellar evolution, is that they are very, very precise, but everything is hidden, because it's really, you cannot follow so many variables in your, I mean, my brain does not do it, and I think most of the brains do not do it.
Cool. Very good. Marcelo, thank you so much for walking us through your very lovely article. Thanks.
No, thank you very much for the invitation. As I said, I was very nervous, because it's like, I mean, I find it difficult to talk about it, and maybe with so many equations, and it's not the kind of thing that you can describe just, a result, just that you measure it. I mean, that would be easier in a way, easier to describe at least.
Right. So you mentioned it a couple of times when you were going through, and so let me just ask, where do you think we go on this topic? Let's say over the next couple of years. This is paper 2 in the series. Do you anticipate paper 3, a paper 4 in this series? Is there observational work that could be done? Just sort of next steps on where do we go as a community over the next couple of years?
Yeah. So I think observational work, not really, because these are simple. So whatever you can test with, I mean, in a way, what you want to do with these toy models is to understand what the detailed models, that there are the ones that you are really comparing with the observation, what they are doing, trying to understand something that, in a way that when you see a result, you can know, this is happening because of that, so that you can really gives you some confidence that the numerical results make sense.
Yes.
And so I think that from the observational point of view, it's not really much to do. On the theoretical side, maybe some people will say that there was no point in doing these 2 papers because this is something I got. This is something I got many times. Is why doing toy models? I mean, numerical, detailed numerical models already tell you the answer. I mean, stars. This is not how I see it and not how I feel it. And the reason why I'm doing them is because this is kind of work that gives me a lot of pleasure, in a way, intellectual pleasure. Well, I mean, they are extremely frustrating on one side, because I mean, the previous one was really frustrating, but because it took me many years to to come to a conclusion. But on the other hand, it's the kind of question that I have since I studied the stellar evolution for the first time. So I want to know the answer. I really have this kind of burning need to know the answer. So regarding where to go from here, so in principle, yeah, my idea would be to go to, at least there are two things that I think could be done. I mean, it's not straightforward to see how they could be done. One of them is to in a way clarify a bit how the blue loops happen. When you go to intermediate mass on massive stars, I mean between 3 and 10 solar, for the audience, let's say between 3 and 10 solar masses during the helium core burning phase, you have this, the star went to the red giant, then during the helium burning phase, core helium burning phase, goes to the blue and then goes back to the red. And this is again something which is related with the fact that the envelope is expanding and contracting, and why is it doing it? So
fair point.
It is well known that the blue loops are fragile in a way. I mean, it's easy that the models this goes away from the models. It's easy to find them back. We know that they happen because cepheids are there, so blue loops should have to be there. But the models sometimes give simulations sometimes do not go through that phase if you don't use the right let's say things in the stereo code. But why and how much do each of them affect? It's not clear. So one of the things I would like to do, and I started reading, but of course I have the other things that are the ones that I do for a living most of the time that I have to do. But so I want to try to use this kind of simple, not the simple toy model of low mass, because these are not low mass, there is no degenerate core, nothing, but the kind of relationship that you have for the burning shell and the mass and radius of the core is the same.
There's something there. Yeah, I can see the relationship between this one and that one. Yeah, very cool.
So I think this is one of the things I would like to do. The other one, which was also one of the things that I had even in mind before even finding something that resembles a solution for the red giant thing, is to have let's say an acceptable explanation of the critical mass at which stars depart from the red giant. You know, stars, you have red giants. If you take a red giant and you take the envelope away, by winds. In fact, this is usually in low mass. Let's say in the first red giant branch, this can happen by binary interactions, so mass transfer. Then you reduce the mass of the envelope, and then at some point the stars starts to evolve to the blue, so they cross the H diagram, and they go to white dwarf. And in AGV stars, or in stars that go through core helium burning and then through the thermal pulses. In AGV stars, you have the same thing. Now by winds. Now it's really this kind of dust-driven winds that they are very intense, and then they erode the whole envelope. But at some point, the envelope is very thin, and then the star goes to. But it's very difficult to find a physical way of saying, okay, now the star is departing the red giant branch. So giving, let's say, some kind of what is the critical mass? But there is a critical mass. It's clear that there is a critical mass. So, but what is the, let's say, try to get a better understanding of what sets this critical mass. You know, the critical mass is depending of the mass of the core. This critical mass of the envelope could be this of the order of 10 to the minus 3, 10 to the minus 5 solar masses. But what sets this particular value? Then I think this is the kind of thing that you could do here, at least with this kind of analysis. Not the same.
Yeah, very cool.
So if you ask me, the things but it's not that I have a very clear picture of how to do it. But I think I would like to continue this kind of series by looking at the blue loops and then the departure from the red giant branch.
Very cool. Very cool. Well, I look forward to seeing some of your work on this topic over the next couple of years, and just generally.
Hopefully, we'll mean in the next couple of years. You know, the first one, since I started trying to find a solution to this day, it took me like close to 15 years to have something that I was happy, because I was finding things that resemble a solution, and then when I was looking at them, I said, but I'm really asking for the. And one of the things I should mention this about this red giant, the first paper is really something that was very, to me, a very enlightening paper was by Sean Faulkner, one of the old guys in Stellar Evolution.
Yeah,
But it was a very obscure paper, very difficult to get. So I had to get it from the library once I was visiting the Max Planck in Germany, because
okay.
I could not find a copy of it. I mean, there was no way to get a copy of that. I mean, at least not here. Also, the post does not work very well, so buying the book itself was not the choice at that time. So so to look for the paper, it really took me some and that paper really, I think that there are some things I do not agree, but the way it is presented is a very funny paper to read, also because it's a proceeding, so with a lot of freedom to write whatever he wanted, clearly, and he wrote it in a very nice literary kind of way. So it's really nice to read, difficult to understand because the mathematics there is very scarce.
Right, it's John.
but the insight is, I mean, the insight, I mean, it really changed my mind and how to look at the problem.
Yeah. No, John was excellent at that. Super. Alrighty, Marcelo, thank you once again.
Okay, no, thank you for the invitation, and I hope this is, I mean, I'm not a complete mess as a speaker. That are the comments activated? Because I can read them below.
That's a different topic. We won't go there. Okay. Very good. All right, everyone. Thank you so much, and I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you. Bye.